Hi, everyone, and welcome to part two of the categorical dependent variables lab. We are picking up right where we left off and moving from where we had a dependent variable with two categories to a dependent variable. Now we're going to talk about three categories, but it would be applicable what we're talking about, for example, if you had four categories or five categories. Now, the primary distinction in terms of kind of modeling choice that you might go with depends on whether those categories are ordered or unordered. In other words, is your dependent variable nominal or is it ordinal? So, way I guess I think about it is if you coded the categories as something like 1, 2, 3, would that indicate some sort of increase, like a changing magnitude, right? If I said like year in college or something like that, the class, like freshman, sophomore, right? If I coded that 1, 2, 3, and so on and so forth, right? We'd call that an ordinal variable. They're increasing over time, and increase in education over time. Whereas a nominal might be something, for example, could be like racial, ethnic identity, gender identity, these types of things where you coded them as 1, 2, 3, right? It wouldn't indicate that 3 is better than 1 or has something more than 1 has, right? There's no inherent order to that variable. So we're going to start with treating our dependent variable, in this case y2, as an unordered categorical variable or as a nominal variable, in which case it's generally appropriate to use multinomial logistic regression is what it's called. Notably, we're going to use the logit linking function for both of these next models I'm going to be talking about, but you could use the probit linking function if you wanted to. One important point to make when they are unordered, basically we have to make comparisons. It's similar kind of when you're dummy coding, right? The reference category is up to you. You just want to make sure that's going to be meaningful. So in this case, I have the variable coded as 0, 1, and 2, and we're going to compare 0 and 1 and 0 and 2, or 0 is that reference category. But you could change that in your specific case. That's just an important point to make. That is entirely up to you. There's not a huge, mathematical difference, but it could be important to your research question to make certain types of comparisons. So we're going to have to install another package first. And then once you install that, we're going to load it. You'll see here again, very similar to the linear and GLM, what we just did. We're just having multinom right here. Otherwise, it's very similar. So let's run that. And then we can get a summary. Now, you'll see that we actually have two sets of coefficients and two sets of standard errors. And again, the reason that is because, remember, we're comparing 0 and 1 and 0 and 2. More or less, we're taking the binary logistic regression model that we just did previously in the other video. We're basically doing two of them and putting them together into one model. So that's why, for example, the x1, we're going to have two coefficients, because it's going to be related to the probability of being 0 or 1 and the probability of being 2 or 0. Now, another thing you might notice is we really don't have a lot of information that we might want here. So first one, we might want to evaluate the overall model fit. So we can do what we previously did and test it against an intercept, or here it'd be intercepts model, and see how our model looks. So a little bit kind of annoying, but you just have to do the work for it. And then things like p-values, odds ratios, also we want, but again, we have to do the work for it. But it's not too bad, just kind of can be a little frustrating. So first one I'm going to do is estimate this model or the intercepts only, because we have two intercepts here, that model. So here, that's why the 1 y2 rests onto 1 right there. It's basically just regressing y2 onto itself is what's happening here. So we can do that, and we have a look at it again. So now we just have the intercepts and the standard errors, and we don't really need to look at it, but just wanted to show that. And now we can test that null model against our hypothesized model. And you could use the ANOVA function that we've used in previous labs, but I want to use this LM test package, which has a variety of helpful things that come with it that we're going to be using. So you want to install that if you don't have it, and then load it. And now we're going to do a likelihood ratio test for our hypothesized model versus the null model. And we get our chi-square, the degrees of freedom, and then we get the p-value. So we interpret this as our hypothesized model being a statistically significant better fit to the data relative to that null or intercepts only model. Now, with a multinomial model, you might want to try to get something similar to that goodness of fit test we did. You can kind of hammer your way into it in a way like this that I'm going to show. Generally, you wouldn't want to do this and report it. There's some reasons why, but generally I just wanted to show it. You could still kind of get at a similar idea, but I wouldn't actually do that or report it in the real world. Just want to illustrate that here. Just looking at the, again, observed and then the predicted. Okay, so now to actually get the p-values, the first thing we want to do is standardize into z-scores or walled z-scores. So I'm just taking the coefficients and then dividing by the standard errors, and those are going to be all the z-scores. So now we have all the z-scores, and then we can take those z-scores and turn them into p-values. So that's what these lines of coding are doing right here. And if I'm doing ×2, I'm doing a two-tail test in this case. So now we have all the p-values and could interpret. Another thing to illustrate with a likelihood ratio test, we're comparing the hypothesized model that had all the independent variables against the intercept only model, but you can test more models against each other than that. So for example, one approach might be to test a model with a predictor and without a predictor and see if there is a difference, right? Does that substantively change the fit of the model? So just to illustrate that one, I'm just going to do that with this x1. Little bit confusing because you see the -2. That's not actually -2. It just means there's 2 degrees of freedom difference here. So just ignore that negative part. We get 2 degrees of freedom. We get the chi-square value and then the p-value. So in this case, for example, if we were using some sort of approach, maybe a stepwise or trying to find a good independent variable, we might add it and then test it, or like we kind of did here, did the full model and then took it out and then see basically what happens, right? Does it significantly change your fit? Now to get those odds ratios, again, we just have to do the exponential. And so I'm just taking all the coefficients, so e to the power of each coefficient, and now I have all the odds ratios. Okay, last one I want to talk about. Let's move to treating the dependent variable as an ordered categorical variable, or in other words, if you had a dependent variable that's ordinal. often called ordinal logistic regression. Again, I'm going to use the Logit link, but you could use the Probit link. Another name that this model sometimes goes by is proportional odds logistic regression. You'll see actually in the package that we use to estimate, the command is POLR. So proportional odds logistic regression. Again, it could be proportional odds probit regression if you wanted to use that. But one point, I'm not going to focus too much on this, but this is something to think about if you are to use such a model. A big core part of this is the proportional odds. So with multinomial, right, we're just comparing the relative odds, this versus that. Is this related to the probability that it's this or that, right, with all of these things. With proportional, and often with an ordinal, like I use the example of being a freshman, then a sophomore, then a junior, something like that. With proportional odds, that's actually an assumption that we make. So generally, we think that the odds are basically the same across any of the comparisons that we might make. So we're going to basically treat it, again, as it is like an ordinal variable. But the idea would be, even if we treated it like a nominal variable in random multinomial, like we just talked about, the odds would be consistent. So for example, x1 might relate to the probability that y2 is 1 versus 0, and as a proportional odds ratio for between 1 and 2. So just wanted to briefly bring that up. I'm not going to focus on it too much, but that it is something to consider. And there's not a perfectly great way to test if that assumption is met. So going to have to install another package here. We're going to use this mass package. So once you install that, we're going to load it. So real quickly, I noted that I coded the y2 as 0, 1, and 2. And you're going to see that when I try to run this, we have an issue. It says, oh, it has to be a factor. So even though it is a factor, right now R is treating it as numeric. So this can be something that comes up every once in a while, so it can be helpful. Sometimes you're going to have to change these things. So that's all I'm doing here. I'm just changing y2. I'm saying, hey, that's actually a factor, and treat it as such. And now we can run this. All right. So now we get our results. Again, the coefficients. You see right here. Then we get intercepts. So now we're broadly interpreting, again, how this relates. X1 not just relates to something like the probability of being 0 versus 1. It's the probability of being 0 versus 1 versus 1 versus 2. And if you had more categories, so on and so forth. So I'm not going to do it to keep things relatively brief here, but as with the multinomial model, you'll see here we really don't get a lot. So you will have to go through that process, that similar process to standardize in order to get p-values. If you want to test against the intercept only or null model, again, you can't do that. You just have to put all the code in, and you just want to adapt it for this specific model, but you could do that. A couple small notes to conclude on that I want to note. I know that I coded these all as numbers, but your data don't necessarily have to be in that format. You know, like it could be text in there, for example. And then you just want to make sure it's specified as a factor. And in terms of things like reference category, I mentioned especially something with like multinomial, it can be really important about what reference category you choose in order to have, you know, some sort of meaningful interpretation. This is something that you can change around. You can re-level and change the reference or reorder things as needed. Last thing, and I tried to note it with the multinomial and ordinal, I was using the logistic approach, the logit linking function, but it is totally possible to use the probit would be the other common one. You can do it, and most of the steps are exactly the same if that was your preference. But again, logit tends to be the more common one I see, so I focused on that one. Well, I hope this lab was helpful to you, and we're going to move forward more of these generalized linear models in the next lab. So I hope to see you there.